This is a tutorial on how to find limits algebraically. Now let's first start off with a basic example. So here we want to find the limit of -3 as x approaches 2. Well, in this case, our function is just a constant value. And when your function is a constant value, it's not going to matter what x value you're approaching. The limit will always be the same. Whether you're approaching this x value, or this one, or any other one, you're always going to be approaching the same value, which is the constant number. So the limit of -3 as x approaches 2 is -3. Because the limit of a function that's constant will always be that constant value. Now let's take this up a notch. Let's see how we find the limit when we have something like this. This time, we want to find the limit of -3x as x approaches 2. And instead of our function being constant, we now have a variable in the mix. And the way that we could find the limit of a monomial function, or a function with just one term, all we need to do is plug in that x value that we're approaching. So in order to find the limit of -3x as x approaches 2, we'll want to plug in that x value we're approaching, which is 2. So now let's just evaluate that. So -3 times 2 will give us a value of -6. So the limit of -3x as x approaches 2 is -6. Now let's bump this up another step. Let's see how we find the limit of a function that has more than one term. Here we want to find the limit of -3x squared plus 7x minus 4 as x approaches 1. Now the way that we could do this algebraically is to sum up all the limits of each term. So we'll want to find the limit of this term, and then add it to the limit of this term, and then add that to the limit of this term. Or you could also say minus the limit of this term. So let's find the limits of each term individually first. So we have -3x squared, and we want to find that limit as x approaches 1. So all we need to do is plug in that x value we're approaching. And when we do that, we have 1 squared, which is 1, and then times -3, which gives us a value of -3. Now let's find the limit of the second term. So this time, we need to find the limit of 7x as x approaches 1. Well, so all we need to do is plug in that x value we're approaching, which is 1. And when we do 7 times 1, we'll get a value of 7. Now we just need to find the limit of this constant as x approaches 1. Well, if you remember from our first example, the limit of a constant as x approaches whatever value is just going to be the value of that constant. So the limit of 4 as x approaches 1 is 4. Now that we found the limits of each individual term, we need to combine each of the limits accordingly. For example, we need to add the limit of the first two terms, and then subtract the last limit. So we have -3 plus 7, which is 4, and then 4 minus 4 ultimately gives us a value of 0. So the limit of this function as x approaches 1 is 0. Now that we've done that, let's try a different example. This time, we want to find the limit of this quantity, -3x minus 5, all being raised to the 1/2 as x approaches -3. Well, the way that we could do this algebraically is first find the limit of the quantity inside the parentheses here. And then whatever that limit ends up being, we could just raise it to the 1/2 afterwards. And then that would give us the limit of this entire function as x approaches this value. So let's first start off by finding the limit of this quantity of negative 3x minus 5. Now again, the way that we would do this is similar to with our previous example, finding the limit of each individual term and then combining them together. So the limit of negative 3x as x approaches negative 3 will be 9. And then the limit of this 5, or negative 5, however you want to look at it, will just be that same value since it's a constant. So now when we combine them together, we get 9 minus 5, which gives us a limit of 4. But remember, this limit is only the limit for the quantity inside the parentheses here. In order to get the limit for our entire function, we need to take this limit and then raise it to that 1/2 power, which is the same thing as doing the square root of 4, which ultimately gives us a value of 2. So the limit of this function that we have here as x approaches negative 3 is 2. Now let's move on to do something a little more complicated. So here with our fifth example, we want to find the limit of x squared minus x minus 6 over x plus 4 as x approaches negative 2. Well, the way that we could do this algebraically is to first find the limit of the numerator and then find the limit of the denominator. And then from there, take that top limit and divide it by the bottom limit. And that will ultimately give you the limit for this entire function. So let's start by finding the limit of the numerator. So we have x squared minus x minus 6. And we want to find the limit as x approaches negative 2. So we'll plug in that x value we're approaching for our x variable. So we have negative 2 squared, which gives us a positive 4, and then minus a negative 2, which becomes a positive 2 because of the double negative, and then we have minus 6. So we have 4 plus 2, which is 6, and then minus 6, giving us a value of 0. So we know that the limit to our numerator is 0. Now let's find the limit of our denominator. So we have x plus 4, and we want to find that limit as x approaches negative 2. So we'll plug in that x value we're approaching. So we have negative 2 plus 4, giving us a value of positive 2. So the limit of our denominator is 2. Now in order to get the limit of our entire function, we just need to take that top limit and divide it by the bottom limit. So the limit of this function that we have will be 0 over 2. Or in other words, 0. Now something important to keep in mind is that when we're working with division or rational functions like this one, finding the limit may not be as nice as this was. So let's take a look at another example. So this time we have a slightly different function that we want to find the limit for. And the principle is still the same. We could take the limit of the top and divide it by the limit of the bottom. But in this case, we know that 0 is our top limit, and we need to find what our new bottom limit is. So we have 2 times x plus 4. And we want to find the limit of that as x approaches negative 2. So we'll plug in negative 2. Now 2 times negative 2 is negative 4. And then when we add 4 to that, we also get a value of 0. Now if we ever have a 0 in the denominator, our function is undefined. So we can't just leave it how it is. This would not be a limit. So we need to use some algebra to manipulate the function first in order to find the limit. And probably one of the most common ways of doing that is by factoring. So for example, we could factor the top part of our function into two binomials. Now, if you don't remember how to do this, you'll have to refer to our tutorial on factoring. Now, in this case, we could take our numerator and factor it out to be x minus 3 times x plus 2. And as for the bottom, we could factor out a 2 from both of these terms, leaving an x plus 2. Now at this point, we could see if there are any terms that are the same on top and bottom. And if that's the case, we could cancel them out. So here, if you notice, we have an x plus 2 on top and an x plus 2 on bottom. So we could cancel those, because when you have the same thing on top and bottom, it cancels to be just the value of 1. Because if you take a number and divide it by itself, that's just 1. So that leaves us with this x minus 3 over 2. So we could use that as our new function for finding the limit. So we have x minus 3 over 2. Now we want to find the limit as x approaches negative 2. So we'll plug in that x value we're approaching. So we have negative 2 minus 3, which gives us a negative 5, and then divided by that limit of 2. So the limit of this function as x approaches negative 2 will be negative 5 halves. Or in other words, the limit of the function as x approaches negative 2 is negative 2.5 if you reduce it into a decimal form. Now for our last example, we're going to look at one more technique for finding the limit of a rational function. Now for finding the limit of this function, it's going to be similar to the last example where we need to use factoring. But this time it's going to require some more thinking and reasoning. But before we do that, you need to remember that our reason for using factoring in the first place was because our denominator was 0. So let's first check our denominator and make sure that it's 0. So if we find the limit of x squared plus x minus 2 as x approaches 1, we'll want to plug in 1 for that x value. So we have 1 squared, which is 1, plus 1, which is 2, and then minus 2 from that does give us 0. So we know that our denominator will be 0. So we do need to use some algebraic techniques to fix that. So let's first start off by factoring our denominator into two binomials. And again, if you don't remember how to do that, please refer to our tutorial on that subject. So in this case, we could factor it out to be x plus 2 times x minus 1. Now as for our numerator, we're going to need to do a little bit of rearranging before we do our factoring. And you'll see why in a minute. So first, I'm going to group the x cubed with the positive 8x. So we have x cubed plus 8x. Now what I want to do with these two is factor them down into their simplest terms. So if we look at both these terms, they share an x. So we could pull an x out, which leaves us with x squared plus 8. Now from here, I need to take the other two terms and group them together. So we have a negative x squared minus 8. So I'll bring them together. So we have negative x squared minus 8. Now from here, they both have a negative 1. So I could factor that negative 1 out, which leaves me with x squared plus 8. Now that is the goal with grouping the numbers together in the numerator. You want to be able to factor out values to where you're left with this same binomial for both groups. So as you could see, our first group left us with an x squared plus 8, and the second group also left us with an x squared plus 8. Now here's where more of the thinking and reasoning comes into play. Now imagine that our binomials here, the x squared plus 8, are like some big variable. Now this is where some more of the thinking and reasoning comes into play. So I'm going to show you another small example on the side here. So say we had 3y minus 2y. Well, our variables here are the same. They're both y's. So what we could do is we could take the coefficient here and combine it with the coefficient here. So we could think of that as 3 minus 2 in the parentheses times our same y value times our same variable. Now if we simplify that, 3 minus 2 leaves us with just 1, or 1y, which is the same thing as 3y minus 2y. Now knowing that, let's apply it for what we have here. So first of all, we have the same variables, or the same quantity, for both terms. And then as coefficients, we have an x and this invisible negative 1. So what we could do is combine those coefficients together. So we have x minus 1 times that quantity that they both share, which is x squared plus 8. So now that we have that, we've officially factored our numerator. So we have x minus 1 times x squared plus 8. Now if you notice, we have a quantity of x minus 1 on top and x minus 1 on bottom. So we could cancel those out, which leaves us with x squared plus 8 over x plus 2. So we're going to use that now to evaluate the limit of our function. So let's do that. We have x squared plus 8 over x plus 2. And we want to evaluate that limit as x approaches 1. So again, we could start with our top portion. So we'll find the limit of x squared plus 8 as x approaches 1, which 1 squared gives us 1, and then 1 plus 8 will give us a limit of 9. Now let's do our denominator. So the limit of x plus 2 as x approaches 1 is 1 plus 2, which gives us 3. So when we reduce this, we find that the limit of this function here as x approaches 1 is 3. Now you know some techniques on how to find limits algebraically.